So we're going to be talking right now about friction, specifically, well, we're going to get deeper into friction. We've talked about it already, but we're going to get a lot deeper into it. And so here's some of the basics. Friction is calculated using the normal force. So like we discussed in class, the amount of friction depends on having a normal force, and the stronger the normal force, then the stronger the friction. So we showed an example where we're holding a book against a wall. So if you're applying a force to this, the wall, if the book is being held in place, then what's holding in place is the friction between the book and the wall. If you don't push on the book hard enough, the book's going to slide down because there won't be enough friction. And so the strength of that friction is increased the harder you push. So there's a direct relationship between the amount of friction and the strength of the normal force. Okay, so there's two types of friction. We have static and kinetic. We've discussed that already. Static friction is equal and opposite to the net force unless the applied force exceeds the maximum capabilities of the static friction. Kinetic friction is always going to be opposite in the direction of the velocity, and is independent of the strength is technically independent of the velocity. And then friction is calculated using the normal force. I said that once already, I'll say it again. Friction depends on the normal force. Okay, so let's kind of go through a visual of this. Alright, so I've got a PowerPoint slide I'm going to put up right now that shows, and these are pictures from the book. So we have a range of scenarios, and we can kind of quantify the forces acting here. So we have an object sitting on a table. There's no friction because there's no force applied to it. Okay, then if we apply a force, if there's enough static friction to keep it in place, then it's going to balance out that force. Let's say that we push harder, so we're going to push a little bit harder. Well, static friction is still bouncing out, and as long as it's capable of bouncing out, it's going to keep pushing even harder until we push beyond what static friction is capable of pushing back with. At that moment, it starts to slide, and the static friction turns into kinetic friction. Okay, and as long as those forces are unbalanced, it's going to accelerate, and then if you push with a little bit less, you can keep it at a constant velocity. That's generally the act of pushing an object looks something like this sequence here. You push until you overcome that static friction turns into kinetic friction, object accelerates, and then you start to push with a little bit less force. And so if you are measuring the amount of force of friction, the force that friction provided as you pulled it, it would look something like this. As you push, the force gets stronger, 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 until suddenly the object kind of breaks loose, and then you notice that frictional force suddenly drops off and gets a lot less. Not necessarily a lot less, but it becomes less, and kind of relatively remains constant from there. Okay, and this is pretty standard no matter what surface it is and what the object is. There's this relationship where static friction is stronger than kinetic friction. Okay, and this has to do with the interactions on the surfaces of the objects. Okay, so we'll talk about that real quick. So friction happens because objects have interactions between their surfaces, and they're not perfectly smooth. Okay, so like if you look at the surface of two objects, they're kind of bumpy. Okay, and then they're kind of scraping against each other when you push them, and so like these little ridges are catching each other. And even when an object is stationary, then there's going to be interaction. So remember that an atom contains a positively charged nucleus and a negatively charged electron on the outside. They have like an electron cloud out here. And so the molecules on the surfaces of these objects are going to interact because of their nuclei and because of their electrons, and they're going to kind of like bond together in some places because of the pressure of the objects against each other. Okay, and so when you push an object, you're basically like shearing off these connections and you're breaking them loose on this like very tiny microscopic scale. Okay, And so so like when things like sit relative to each other, they sit on top of each other, then they have a chance to like bond together a little bit. And that's why static friction is a little bit stronger than kinetic friction. Once kinetic friction happens, they're not bonded together anymore, just these little like jagged edges are catching against each other. And that's essentially what's going on. Okay? Okay, so now we're going to work through this problem. There's a block lying on the floor, and the question is, what is the magnitude of the frictional force on it from the floor? Well, it would be 0 because it doesn't have any force to resist. If it's just sitting there, there's no reason for there to be friction unless there's something pushing against it. If we now push with a force of 5 newtons, but the block doesn't move, how much frictional force would there be now? It will be 5 newtons balancing out that push. If the maximum value of the static frictional force on the block is 10 newtons, will the block move if a force of 8 newtons is applied horizontally? So if we now push with 8 newtons, is it going to move yet? What if we apply a force of 12 newtons? What happens now? In part C, where we were pushing with 8 newtons, with how much force was friction pushing back? Alright, so in C, it would be pushing back with 8 newtons to balance out the amount of push. If we apply a force of 12 newtons, the block is now going to accelerate because we're pushing with a strength greater than the ability of friction to resist. Okay, so let's go ahead and focus again on the relationship now between friction and the normal force. Out that friction, what physicists like to say is that friction is fun, okay? Because friction is related to proportionally the amount of normal force, okay? And so if this is representative of the normal force that an object experiences between the surface where there's friction, and this is the frictional force, then we call this value right here the coefficient of friction. Okay? And I spelled it wrong. There you go. Of friction. Okay? And this is dependent. This is a property of surfaces. Okay? So different surfaces had different coefficients of friction. Okay? And these are approximations. This is a model in every sense of the word, in that a coefficient of friction is kind of this average quantification of the amount of friction a surface has, okay? And that this is really just getting at the idea that more normal force means more friction, less normal force means less friction. And we can do a pretty good job approximating frictional force using this equation, okay? So what we can do, though, is if we know the normal force on something, then and we know its coefficient of friction, then we can actually calculate how much friction there is. And the other thing we can do, if we can measure friction and we know the strength of the normal force, then we could find out the coefficient of friction for a particular surface. Okay, so we're going to look at an example of that now. So we'll look at this problem right here, okay, in which we have a car's wheels are locked during emergency braking. Skid marks reveal cold welding occurred in the slide, which means it's sliding. Okay, the longest skid marks ever recorded are 290 meters long. Assuming coefficient of friction was 0.6 meters, and the car's acceleration was constant, how fast was the car going when the wheels locked? Okay, so the way that we're going to do this is we're basically going to we have a net force or a free body diagram here. Okay, in this case, since it's balanced up and down, and it's on a horizontal surface, we're going to assume that the normal force is equal to the weight. And so what we can say here is, okay, the sum of the forces in the horizontal direction, if we want to find acceleration, then we can say MA. And so we can say that the sum of the forces equal to MA. Well, the only force acting in this direction, let's say that this way is positive. Okay, well, the only force acting in this plane is kinetic friction, so Fk. Well, we know that kinetic friction is, or the coefficient of kinetic friction is 0.6, and we know from earlier that friction is equal to the coefficient of friction times the normal force. So in this case, it's going to be mu times mg. So we can say, okay, then ma is equal to mu times mg. These will cancel out, and so a is equal to 0.6 times g, or 0.6 times 9.8. For the sake of this, we'll just say that g is equal to 10. So that means we have an acceleration, and I apologize, we made a mistake here. If this way is positive, then this is negative, which means that this is negative, which means that this is negative, so we get negative 6 meters per second squared. So if we want to find now how fast the car was going, we could do kinematics. Use this equation, v squared equals v naught squared plus 2. I don't know what just happened there. Alright, plus 2 times a times x. We know that a is negative 6, and then x is 290 meters. So if v squared is 0, then negative v naught squared would be equal to negative 12 times 290, which is 3,480. This would be negative, so the negatives disappear, we take the square root and get a velocity of 59 meters per second, okay, which is approximately 130 miles per hour, okay. So this car was going like 130 miles per hour, it locked out its wheels and skidded for 290 meters, which is basically 3/4 of the way around a track, okay. And so there you go, that's friction, okay. We're going to do one more together and then we'll finish off this video, okay. We'll save this one for the next video though. So let's say that we have a 5 kilogram object that's sliding across the floor. We give it, maybe we've given a push, it's going 4 meters per second, and it's going to slide to a stop, and it's going to take 2 meters to stop. Okay, and so the question is, well, what is the coefficient of kinetic friction between this box and the floor? Okay, so in order to do this, we would need to know acceleration. And so let's start by finding the acceleration of this box. So if we know this initial velocity, we know it's going to travel 2 meters while it comes to a rest. What would be the acceleration of this box? Hopefully you got that there was an acceleration of about negative 4 meters per second squared. The next step is going to be to write a net force equation. So if this object has weight, has a normal force, is experiencing kinetic friction causing it to slow down, what would be the net force equation for this horizontal plane? We'd say m times a is equal to negative F. We can substitute that for a. Remember that F is equal to mu times the weight, mg. Okay, so this would be equal to negative mu mg. This is equal to ma. Alright, so I'm going to have you go ahead and tell me what the coefficient of kinetic friction is. So we put in negative 4, the m's divide out, equals negative mu times g. If we round g to 10, we get that mu is equal to about 0.4. Now what you'll notice is this. Well, let's go that. Yeah, it's equal to 0.4. Okay, so let's go back to our friction equation. The units for mu are like this. This is friction, this is normal force, both measured in newtons. So when we divide these over, we get units of newtons divided by newtons. But this is tricky. These technically don't directly cancel out because these are newtons up and down, whereas these are newtons, I guess, or these are newtons perpendicular, or these are newtons rather parallel to the surface, whereas this is perpendicular to the surface. And so that since they're in different directions, the canceling gets kind of weird.